Hello, folks of the internet. I hope you've been able to stay safe and productive during our enforced study break. I'm coming now with a video that's not going to be part of the Differential Topology Series that I've been working on up until now, that has been on a pretty extended hiatus. And that is because I mentioned this in a comment response to one of those videos, that I have since found a great deal of very important papers that discuss kind of a more general direction to discuss differential topology from. So I'm going to renew my series soon, starting from that perspective, from those more general foundations, and then I'll eventually work up to all of this stuff involving manifolds that I was discussing previously. So that's what's going on that end. This is going to be a very different series, starting from, well, I wanted to say the bottom, but it's not quite the bottom. It's close to the bottom of mathematics as I am willing to get, and as most people are willing to listen to. So I'm going to start a introductory series where I begin by teaching logic. You see up here on the board, I've got a couple examples of different statements. And using that, an understanding of logic, we're going to begin to work our way into the language of mathematics, starting with set theory, learning how to prove things in pure mathematics so that we can then move on to the harder subjects like differential topology or even just general point set topology for those of us who haven't already had some sort of background established. So that is the goal for this series, is to make something that a reasonably lucid person could tune into, extract enough information to go off and start reading mathematical literature, or even just start learning new higher subjects from other YouTube videos. So without any further explanation for what's going on here, let's talk about logic. Now, logic can roughly be defined as a process or a system wherein I can go about verifying that an argument that someone makes works. Ultimately, what we're talking about when we're doing logic is whether or not statements, claims that are made, are true or not, and whether or not an argument proposed that stands on those claims is actually valid, whether or not it produces the conclusion that you claim that it does. And, all arguments, no matter how complicated and sophisticated they are, they're all actually made out of the same simple building blocks. So like any introductory anything, we're going to start with those building blocks and understand how they work, and then see some examples where these arguments have been made from these simple building blocks and where these simple building blocks have been applied in important arguments in history. So let's take a look at some of these basic building blocks. And many of these are going to be words that, all of these are going to be words that we use in our day-to-day speech. But when we use them in mathematics, we're going to be very, very specific, which is why I have these things. They're called truth tables written down. They tell us whether or not the truth, or whether or not a statement is true based on the truth of its components. So, the and statement. You probably use the word and all the time, and it means in mathematics essentially probably what you think it means. If I say the sky is blue and it's raining outside, well, in order for that statement that I just told you, the sky is blue and it's raining outside, in order for that to be true, it must both be blue, the sky, and it must also be raining outside, which would be quite difficult. But that would be the criteria that needs to be met in order for that and statement to be true. Both of its components must be true, which is what we can see illustrated up here on this truth table. I have the word that we use for the statement to the left, and then the symbol that we generally use when writing things symbolically, because as mathematicians we're lazy and we don't like to write lots of things. And then on either side of the table I have the name of the input that the column is corresponding to the changes in. So over here I have Q being true and Q being false, P being false and P being true. And we can see that, just like I said, when both of the components of my and statement, P and Q, when they are both true, then my and statement is also true. But in any other circumstance, either P or Q being false, or both of them being false, then my and statement is false necessarily. So the and statement requires, like you might imagine, both P and Q to be true. So now that we've gotten kind of a basic idea for how the structure of these truth tables works, I can do this next one, the or statement, a whole lot more quickly and just talk about the nature of the statement itself. So once again, or is another word that we use all the time in common parlance, and it means that almost essentially what you think it means. It's just really, really specific. So if P or Q is true, then I don't need both of them to be true, like is suggested when I say and. I really only need one of them to be true. Both of them can be true, because if one of them is true, then P or Q is certainly true. I can pick either one, and it would certainly still be true. But if they're both false, if P and Q are both false, and I ask, P or Q true? The question has got to be no, because you can take a look at P or you can take a look at Q, and the answer is always F. It's always false. So where and was the most exclusive statement, he required both of his components to be true in order to be true. Or is the opposite. He requires both of his components to be false in order to be false. He's got the easiest requirements as far as being true here. I need, between these two statements, I only need one of his components to be true. So if I've got a false statement and I just slap an or true statement onto it, that automatically makes a true statement, no matter how ridiculous the false statement that I'm oring with. For example, if I say the sky is blue or it rains pigs when I cry, that's a pretty crazy claim to make. But thankfully, that claim, the sky is blue or it rains pigs when I cry, is actually true, because regardless of how absolutely ridiculous that second statement is, believe me, it doesn't happen when I cry. I only need one of the components to be true to be living in this case here. So that's and or, the most exclusive truth conjunction and the least exclusive truth conjunction. So that's and or, and they work essentially how you expect them to. Now, for the most important one, the one you would have seen if you've done any programming, and certainly if you've ever made an argument with someone, you've uttered the words if something, then something else, because it's just kind of the natural way that you set up what's known as an implication, which is another name for this statement. It's often read P implies Q. So now let's talk a little bit about what that means. If P is true, then Q is true. So already, just by the way that I'm saying that, it kind of sounds like if P is true, then Q is true is asking a sequence of things. It's asking me to check if P is true first, and then if that's the case, it's asking me to check afterwards if Q is true. So it turns out that ordering is really important, because if I check P to be true and it turns out to be false, then I don't have to do any more work from that point forward. If what's called the hypothesis of your implication, the hypothesis of your if-then statement, is untrue, then the implication is automatically true. There's another way to make completely ridiculous statements that are still in fact true. So now I could go with just taking my ridiculous example for last time, so that I don't have to be more creative. I could say that if it rains pigs when I cry, then I'm the master of the universe. then I'm omnipotent. And you might think to yourself, well, that's crazy. And it absolutely is a completely ridiculous line of words. But because the hypothesis of my implication was false, it's certainly not true that when I cry, pigs rain from the sky. Since that's false, it is true that that implication holds. If, when I cry, pigs rain from the sky, then I am in fact the master of the universe. That's a pretty easy way to gain omnipotence, if I have to say so myself. But okay, so that's just another way that logic allows us to make absolutely ridiculous statements that are true, and that's one of the reasons why I say, we have to be very careful that these things have specific meanings, because those are what we're going to be exploiting when we're actually proving things in mathematics. So now that we've gotten the first three out of the way, the ones that have two inputs, let's just talk about the very last one, the not operation, which it almost goes without saying kind of how it works. does the opposite of whatever you say. So just like when you say not before something, you mean opposed to that, or, for lack of a better word, not that. So not true is false, and not false is true, because that's sort of what we mean by those things. Truth and false are mutually exclusive. You can't be both or neither, and so if you are not one, you are the other. And that one, thankfully, doesn't require all too much explanation. So there are more ways to conjoin logical statements like P and Q. Where logical statements, I should have mentioned this earlier, logical statements like P and Q, they are things that have a truth value. So they're either true or false, but not both or neither. So as soon as I have these guys, I can build most basic arguments. There are a couple more that I haven't put on this list, but understanding these makes understanding those absolutely a walk in the park. You can look them up and their truth tables whenever you feel like it. And there's you won't be using them quite as commonly as you'll be using these. And the really historical examples that I have to show you today will only be making use of these logical conjunctions. So now that we've got an idea of what language we're allowed to speak, we're allowed to say the words and, or, not, and if then, we could also say true and false. Let's actually take a break from doing philosophy, which is what we're doing right now, and go back to math. So I'm going to pick out some really awesome, well, what I think are really awesome proofs, and a couple other mathematicians agree with me, and we're going to talk about where all of these things are showing up in these proofs, and how exactly it is that we're making use of what we've talked about here, the structure of these statements, how we make use of that when we're actually demonstrating the truth of a claim. All right, so now that we've got something of an idea about what all these words mean, and, or, not, if, then, let's start to look at why we as mathematicians or scientists might actually care about them. We talk about simple things that, or at least in mathematics, simple things, the things that we can define, like triangles being polygons that only have 3 sides, quadrilaterals, those with 4 sides, and so on. Things that are super nice and exact, like numbers that are totally unambiguous, and areas are an example of a number that we assign to parts of space. A very, very important theorem to do with area in mathematics, one that I'm sure basically everyone has heard about, is the Pythagorean theorem. In case you don't recall, what that tells you is that if you have a triangle which is right, and by that I mean, I don't mean that it's correct. Triangles don't tend to have many opinions on things. By that I mean that it's got one angle which is exactly 90 degrees. It makes a perfect box corner. All right. And in fact, one of the ways that these things were initially defined by the Greeks was that you could put 4 of them around any one spot, and they will all be exactly identical. And if you take 4 corners of a box and put them together, you will see that they were in fact correct, because they're 360 degrees in a circle, based on the fact that we have cut them up into 4 90-degree sections. Okay. So with all of that prelude out of the way, let's go on to how all of the logic we just learned can actually help us talk about whether or not a claim like this is true. So first, let's regard what sort of statement this is. This is an implication, because it starts with an if. It goes on to give me some sort of statement that has a truth value, and then it continues with then, and tells me some other statement with some other truth value. And if I am able to show, just based on our truth table that we were looking at last time, if I'm able to show that whenever this first part is true, that the second part must be true, then I know that my whole implication, if the angle is equal to 90 degrees, then a squared plus b squared is equal to c squared, then I know that whole implication statement is true. I don't need to worry about the case where the angle is not equal to 90 degrees, because if you go back when we were talking about if-then statements, if the hypothesis of our implication of our if-then statement is untrue, we have no more work to do because our implication is automatically true at that point. We call it vacuously true. It's boring, but it works. All right, so let's talk about that then. In order to prove this statement, if P here, I'll say P is the angle A is equal to 90 degrees, then Q, A squared plus B squared is equal to C squared, I have to go through the following procedure. I'm going to assume the first statement is true. That will put me in that case that I was just talking to you about, where the hypothesis is the true statement. Then I'm going to use deduction, and deduction only. I'm going to see all of the things that follow exactly from the thing that I just assumed to be true, that this angle was 90 degrees. And this is going to require us knowing a little bit of math, but don't worry if you're not especially acquainted. I'm going to explain every step in as small and intuitive a detail as I possibly can so that it can be something that we can all connect with, even though at this point, ostensibly, we have not learned any math. So let's get started with that then. So we are going to assume that we are given some triangle, like this one right here, where this angle, ooh, and I should, gosh, I did this with a previous triangle, you can tell, and then redrew all of these things. It's going to actually be that my angle C is 90 degrees, because that's the one I have drawn down here to be 90. And that's what I mean by putting a box on this corner. That is an angle which is 90 degrees. So we are going to assume that claim. We're going to assume that this angle C is equal to 90 degrees. And now I'm going to start taking some steps that will eventually show that this number is equal to this number. And this is the magic of proofs. It's not always obvious how you're going to get from the thing you assumed to the place you're going, but the more you know about those things, the more obvious it becomes. So let's start with the fact that the only fact that I have, which is that C is a right angle. Now, there are some shapes that I know about that I have a pretty easy time calculating the area of. They have to do with right angles, and those shapes are squares. So just off of the intuition that I am interested in squares because they're a whole lot easier to deal with area-wise, I am going to take this triangle that we've got, and I'm going to copy him 4 times. There's nothing wrong with that. You've seen him once before. There's nothing wrong with imagining him being somewhere else. He's the same triangle still. And taking those 4 triangles, I'm going to stick them together end to end so that they create this square here where side A goes into the side B of the next triangle, which has been lent up on its side, and that same thing will go on all throughout. I'm gonna have to correct all of my pictures all the way down. This is awful. Alrighty. So yes. So I've got my triangle being rotated by 90 degrees every time I attach it, and that's going to create this square. And it is a square because each one of its angles in the corner here is 90 degrees. That was my hypothesis. And each one of its side lengths are exactly the same because they're always going to be A plus B, the short side of my triangle plus the long side of, the long side, not the hypotenuse of my triangle. And so this object in here is certainly a square. And in fact, this object, this quadrilateral inside of my square, is also a square. And the reason for that is now I'm going to have to, this is where I'm going to have to bring in some of that math that I mentioned. A triangle, like this one we have here, has a special property that all of the angles inside of it, if you added up that number, you would get 180 degrees, which happens to just be 2 of the 90-degree angles that we specified we know we have one of when we claimed that this thing was a right triangle. So, and also, not only is 180 degrees the angle sum inside a triangle, it is also exactly the angle sum of lines that, or of rays rather, that emanate from a straight line. So if I got this line here and it's straight, and I took a whole bunch of rays and just pointed them out from a point, and added up all the angles, I would always get 180 degrees. 180 degrees is the same thing as turning around. It adds up to a full reverse. So that means that these two angles in here, they add up to 90 degrees because the total angle sum of this triangle is 180, and this angle in here is 90, meaning these two have to add up to 90 in order for the total to be 180. Now that means, since those are the same angles that are occurring right here, that these two parts of my angle sum go up to 90 degrees. But since there has to be 180 degrees at the angle sum for any set of rays emanating from a line, like we've got here, that means that this corner that I've written in here as a right angle is in fact a right angle. It must be in order for that angle sum to be 180. And then since all of these angles are the same because they were made from the same procedure, all of those other angles are 90 degrees as well. So I've got an object here with all sides length c and all angles 90 degrees. This is a square side length c inside of my square, side length a plus b, which tells me this area in here is exactly c squared, which I've written to the side here. So I've got this square that I've made out of the 4 copies of the triangle that we started with, and we know that the square inside is exactly c squared. And all I did to construct this, the only thing that I've used so far is the fact that I've got a 90 degree angle, that was what I assumed, and that the sum of the angles in a triangle, or of the angles formed by rays emanating from a straight line, those are both 180. Those are 2 black box facts that I've just pulled out of my hair here to show you guys. But if you're willing to believe me, then the only thing that I've really done is just apply the right angle assumption that we started out with, and that's how proofs work. The only other things that I can pull in are things that I know are true all the time, like that angle sum jargon that I pulled out a second ago. So we've got c squared, which is one of the numbers that I was trying to characterize. So this is a sign that I'm moving in the correct direction. So now, to get to a squared plus b squared, that other quantity that I wanted to get to, I'm going to shift around these triangles. And I would like you, obviously we haven't gone through all of the theory yet. We're right at the beginning. We haven't gone through all the theory yet to know why exactly this works. But you'll have to believe me, just from your own intuitive experience with space, that when you take an object like a triangle and you just slide it around through space, you don't actually change any of the measurements on that thing. You don't change any of its side lengths. You don't change the area inside of it. Just picking something up and translating it around or rotating it in space, these are motions which have a very special name in geometry. We call them isometries. And the name is not so important, but what is important is that none of those measurements that I was just talking about change when I perform them. So I can perform them with impunity in some sort of proof like this without having to worry about the area inside my box here ever changing. So let's do some of those and know that all of the area inside of this square, which is not contained in these triangles, has to be c squared, because I'm only going to be performing isometries from this point forward. Okay, and so the first isometry that I'm going to perform, I'm going to translate this triangle. I'm just going to take it and slide it down, just like we could if these were wooden blocks where I could just slide it across. And when I do that, because I've taken an exact copy of a right triangle with itself, I know that, remember, this angle and this angle add up to 90 degrees. That was one of the things that I was going through a huge spiel about earlier. So that means when I stick these 2 triangles together, because these angles and these angles are the ones that I'm talking about, they're just from different triangles, but they still correspond to the same angles, these guys also have to add up to 90 degrees. So this makes a rectangle. I know it does because these guys were already 90 degrees. And it makes a rectangle with side length A for its long side and side length B for its short side. And once again, I haven't changed this area. It looks a whole lot different now because it's shaped differently, but it is in fact still c squared because I didn't change the area of this triangle when I slid it down. And so the area of this big square minus the area of all the triangles inside is still the same, hasn't changed. Alrighty, and now it's probably not too hard to see what set of moves that I would want to take next. I'm just going to take these two triangles here, and I'm going to slide them together up into this corner here, which you can see that I've done. And by the time we've done that, now our proof is actually pretty much finished. Because if we look inside here, remember we were creating rectangles inside this square. The argument that I gave over here will also work when I slide them together over there. And because then I've got a collection of rectangles inside of a square, the only place where these corners are hitting each other, they can only ever meet at 90 degree angles. If they weren't meeting at 90 degree angles, one of these angles inside here would have to not be 90 degrees, and we could find it. So every single one of these guys is meeting at a 90 degree angle, and because this rectangle has side length A on this side, just as this rectangle does, because they were formed from the same triangles, that means that this top square up in this portion of my larger controlling square, this guy has got to be a square with side length A on all sides. Just like in my bottom corner, I'll have a square with side length B on all sides. And now that means that I've got this square, A squared, and this square, B squared. They're both inside of my controlling square. They are exactly the area inside of it minus the triangles. But recall that the area inside of this big square minus all the triangles is exactly c squared. That was the first thing that we found out. And the only thing that I did to get to this point was slide triangles around, but that doesn't change the area inside. So that means that this number, a squared plus b squared, has to be the same as this number, c squared. Or a squared plus b squared, yeah. That number has to be equal to c squared. All right, so that was, it's a lot of talking, because really when you want to explain a proof well, especially to folks who don't have a super, super deep background, the goal is going to be to give more detail that is kind of more intuitive as opposed to less detail that is hidden behind big scary words. But now that I have gone through the kind of through the roots, through the weeds explanation, let's just take a step back and talk about what we did. So we started out by assuming the hypothesis that that angle C was 90 degrees. I did a whole lot of mishmash where I took advantage of that angle that I had to build things, squares and rectangles and stuff that I knew I needed to have 90 degree angles in order to construct. After a long diatribe, a long explanation, I was able to use those right angles to start out with a shape that had area c squared and turn it into a shape that I knew had area a squared plus b squared. I showed, and then I told you that meant that those quantities had to be the same. And to strip out all of those intervening steps would be to tell you that what I did was I assumed that that angle C was right. And then from that point, I deduced that C squared was equal to A squared plus B squared. Which, that's how I started out, but now you can probably see a little bit better what I mean. This hypothesis, it's a nugget, it's a starting out point. I can start throwing it at things, and potentially it will give me something back, like it did with this square mumbo jumbo. And at the end of it, if I can manage to get exactly the claim that I'm producing, then that's the proof. That's it. We're all done. And it's very, very specific. It always follows, in this case, when we're proving an if-then, it always follows, I assume my hypothesis, and then I prove my conclusion. If I assume anything besides my hypothesis, I haven't proven my claim. I've proven the claim if something and the thing that I also assumed, then my conclusion. So I can only assume what the hypothesis says, and that's the only information that I can use, aside from stuff that I already know is true no matter what, in order to arrive at my conclusion. But as soon as I have, that is a proven statement. And now, this thing the Pythagorean theorem, it is exactly one of those other true statements that I can go off and apply to other things, just like the angle sum nonsense that I brought up earlier. So that's a sort of like the way that the game of mathematics is played. We start from a bunch of rules and definitions that we all agree on. We build statements like this from them that we know are true, and then we just keep building more and more on top so that we can get cooler and cooler things that are harder and harder to see from the bottom from our definitions. So that's a really famous and proof-wise a pretty fun example of an if-then statement. So now that we've taken a look at one of those, let's go take a look at proving some of our other statements. So now that we've seen a really famous if-then statement and also what the procedure for proving one of those guys is, assuming the hypothesis and then deducing the conclusion from it, now let's talk a bit about the other statement that was on the bottom of my board, the not statement, because that is probably the other most important, and in order are significant, and I'll be using them, and I'll even show proofs for examples of them, but it's pretty obvious how they work, and it's especially proving them is not too confusing. Whereas the if-then, it's got a procedure that's not obvious if you don't just stare at the truth table forever, and not this thing that I'm about to show you. This actually took a philosophical innovation on the part of an ancient Greek by the name of Zeno, or at least I believe he's the one who popularized this technique, and it's what's known as a proof by contradiction, or indirect proof. Essentially, in order to prove this not statement, I'm going to take advantage of one of those definitions that I gave you earlier for what statements are. A statement is a thing that is true or false, but not both or neither. The idea of having a statement that is true and false, or not one of the two, makes no sense, because that is how we define them. So, if I can show that a statement is true and false from some series of assumptions, then those assumptions must be incompatible with one another. They cannot be true, because if they were, then my statement wouldn't be a statement. So, this is the principle of non-contradiction. Statements must be statements, by definition. They must either be true or false. And so, if I can assume some hypothesis and then derive a contradiction, which we symbolize like that, then I know for a fact that my hypothesis is ridiculous. It cannot hold. It must be false. For if it were not, then a statement wouldn't be a statement. All right. So let's take a look at this I think this is one of the coolest theorems ever, but I am a bit of a math nerd, but this is coming straight from ancient Greece, the idea of the irrationality of the square root of 2. And I've got this written down in two different ways so we can kind of see the suppressed not statement notation in here, because oftentimes when we're talking, we say things in different ways. We don't always want to say not that. We don't always want to say a number is not rational. Sometimes we want to just say it's irrational. We, for the sake of our audience, we will occasionally change the way we say things. And just so you're all clear, whenever you see a statement like this, it is still built out of the components that we're used to. It just might require a little translation. And that's something that we're going to work on next time once we kind of have an idea of why we look at these things and why we're using logic. Then I will show you the absolute magic powers that it grants us in terms of converting arguments from unprovable forms into provable forms, into forms that are super, super easy for you to tackle. So that's an example of what's going on here. I'm writing 2 is irrational, which is the same thing as saying not 2 is rational, because those are just opposite statements. And so now, just like with the previous Pythagorean theorem, I'm going to prove this guy for you, but unlike the Pythagorean theorem, I don't need to assume a hypothesis and then prove a conclusion. Like I said, I'm going to try to contradict myself. I want to arrive at this statement being true. So in order to use contradiction, I'm going to assume the opposite of this statement, the statement that I'm trying to show is false, and then derive that contradiction that I was talking about. If I start with something that I don't want to be true, and I'm able to find a contradiction, like I said before, that means that my hypothesis must be false. It can't be the thing that's right, and so the opposite of it, the thing that I wanted to be true, must be true. All right, so let's get started then. I want 2 pi, or the square root of 2, not 2 pi. The square root of 2 is irrational. I want this to be true, so like I said, I'm going to start by assuming that 2 is actually a rational number, something that I believe is false. And then I'm going to just start applying this, just like I did with the right angle hypothesis in the Pythagorean theorem, in order to eventually get to this contradiction in this case instead of a conclusion. So I know, just by the meaning of the word rational, that what it means to be rational is actually that there is a fraction that represents you. So if square root of 2 is a rational number, then that tells me that there is a fraction pq for some integers p and q, and they don't just have to be any p and q that does this. I'm specifically going to choose the p and q which makes this fraction the smallest, the one where they have no common factors. Because if this fraction exists, if I can write down the square root of 2, then I can always just remove the common factors from both the top and the bottom, if there are any. So I'm just going to assume that I've already done that, and we're going to proceed forward with this fraction representation for the square root of 2, where we know that the integers p and q, they're relatively prime to one another. They don't have any factors because I've already done the simplification step, so this fraction is as small as possible. Okay, so then, using this equation, and just doing what my math brain is screaming at me, whenever I see a square root, I just want to get rid of it. I hate those things. So I'm going to connect a whole bunch of my steps here by implication arrows, just to let you know what I'm doing. And these implication arrows are true, by the way. It is true that if this equation holds, then this equation holds, because all I did to get from one to the other is square both sides, and the square of equal things is equal. So I'll square both sides. That will bring me to this equation. And this implies that p is even. And now that's less clear, but you can actually figure that out just by taking some even and odd numbers and squaring them in your head. If you square an odd number, you only ever get an odd number as a result. If you square an even number, you only ever get an even number as a result. So that means if I'm squaring a number p, and I'm getting an even number as a result, because that's what this is, it's 2 times some other integer, then it must be that p is even. And you can do this one for yourself. And obviously this isn't proper proof technique. You can't just test a couple examples and be sure of it. But it is in fact the case that if you square an odd number, you will only ever get an odd number. And if you square an even number, you only ever get another even number. And so that means for a fact, p has to be even. And just so you're all clear, what it means to be even is that p is equal to 2r. To be odd would mean to be equal to 2r minus 1 or 2r plus 1. One off from an even number. And if you feel like proving that claim that I just made about the square of even numbers being even and the square of odd numbers being always odd, you can do that for yourself right now. Just take the definition of even that I gave you and the definition of odd that I gave you, which is just this thing plus or minus 1, and then square them and see whether or not the squares that you get satisfy the even and odd definition that I started you out with. All right, so, but just taking it as a black box for now, that squaring odd numbers give me odd numbers and squaring even numbers gives me even numbers, I now have deduced that p must be an even number. It must be equal to 2 times some integer r. But if that's the case, remember I've got this equation here. We know it's true. It was one of my steps. And that step that I just found was true, so I've got an and statement showing up here, that equation and that equation. Together, they imply this set of equations. Why? Because I'm just substituting in equal things for equal things. Things that are equal by the transitive property of equality, so I can always just substitute things in as I feel like. And if I do that, if I take the p that I'm getting from my second claim in my and statement, and I substitute that into my first claim in my and statement, well, then I get 2 times q squared is equal to 4r squared. There's a factor of 2 on either side of that, so I can cancel it out. And when I do, I end up at the same sort of equation that told me that p was even. Except now it's going to be telling me that q is even. And this is the problem that I wanted to find. Remember, I set out to derive a contradiction, a statement that was saying that that was being said to be true and false simultaneously. So where is that going on here? All I've got is that p and q are even, right? Not exactly, because at the very beginning, I assumed that p and q were integers with no common factors. That was why I got p and q, or they were the minimal representation for square root of 2 that I could find. But they can't have no common factors and both be even. Why? Well, because if something's even, then it's equal to 2 times something. So if q is equal to 2 times something, and p is equal to 2 times something, well, I should be able to divide out that common factor. They clearly have a common factor, a factor of 2, but that contradicts my assumption that they have no common factors. It can't be true that they have common factors and have a common factor of 2. This is a contradiction. And how did I get here? How did I get to this contradiction? Every single one of these steps was true. I have to go back to the only step that I'm not sure about, which is the very beginning. Assume the square root of 2 is rational. That's the only step that I am unsure of, because everything that came afterwards was absolutely a true statement. Therefore, in order to make sense of this contradiction that I have arrived at, I have to reject my hypothesis. I have to say, well, in order for math in the universe to make sense, as it does, it must be that 2 is irrational. Quotat demonstratum. There we go. So that is an example of one of these not proofs. And you don't necessarily always prove them by contradiction, but contradiction is one of the available ways. And it's especially great when the thing that you're trying to prove is very, very difficult to do directly. So I'm not going to do it today, but to just give you an example of a proof that's difficult to do directly that works on this exact same principle. The proof that Euclid gave of the infinitude of prime numbers is a prime example of what I'm talking about here, and another beautiful example of a contradiction proof, or a proof by contradiction, as it were. The difference between what I'm doing here in this proof, where I'm trying to show a number isn't a type of number, and the infinitude of primes that Euclid was doing, is that Euclid isn't trying to show that the prime numbers belong to any particular set. No. He's trying to show you that you can't run out of prime numbers. If you give him a finite set of prime numbers and you tell him this is all the primes, he will come and find you another prime number and give that one to you and say, no, it wasn't, you're wrong. And he can always do that, and so there are infinitely many primes. Now, that is a really, really hard claim to go about demonstrating directly. Why? Well, to directly demonstrate the existence of infinitely many things means producing infinitely many things. Being that we will only ever exist for a finite period of time, that's rather a challenge for us that live, for those mortals among us. So we have to come up with a smarter way of doing that, the indirect way of doing that. Instead of going out and proving that there are infinitely many primes by finding infinitely many of them for you, Euclid does proof by contradiction. He assumes that there was, in fact, a finite set of primes that is everything, that is all the primes. And then he has a procedure to take that set of primes that you give him and construct a new prime from them. That is bigger than all of your other primes, therefore none on your list, and so primes are infinite. Because you can always take, and it actually kind of gives you a procedure for infinitely generating primes. It's not all of the primes. We're not that far into number theory yet, unfortunately, thousands of years in, and we still don't have a formula for the prime numbers. But you can at least generate as many of them as you want, given any prior set of them. So that is another example of where this idea of proving things indirectly is super, super useful. And so now that we have seen Now that we've seen the implication, the if-then statement proven, and we've seen a not statement proven, I suppose it's time to wrap up with ands and ors then. Here we are. This one, unfortunately, isn't like super historically relevant because I didn't have any super historically important and statements off the top of my head. Now I'm sure you could find any, or artificially create them by just taking two really important statements and then putting and between them. I didn't want to do that because I didn't want to be non-canonical. I wanted to pick something that was actually just already established as a nice example in canon that other mathematicians already like besides me, because that way I wouldn't be imposing my own biases of mathematical beauty. There's some sort of a compromise with the rest of the mathematical community on the other ones, but this is just an and statement. So, and in order to do it, I had to pick out a word from algebra that some of you might not know. So let me first define my terms before I try to prove that 0 and 1 are idempotent. So first let me explain that an element A of some sort of system of numbers, we'll call them right now, an element is called idempotent if whenever I square it, I just get itself back, which I'm sure you can guess what that means, what will happen if I raise it to the nth power. No matter what power I raise it to, I always just get the same thing. Okay, so that's what it means to be idempotent. You are unaffected by operation with yourself. And 1 and 0 are both idempotent elements. This is in an and statement. You can kind of see it from the fact that there's an and in the middle, but it doesn't look like P and Q right now. The way I would do that, it's just kind of from the way I've written it, the way you would make it look like P and Q would be to say 0 is idempotent and 1 is idempotent, which is a whole lot more explicit where the and statement is conjoining those two, but it's a whole lot more to say. As soon as I've said idempotent once, really, it's just too many times. So that's how I'm writing it, but you can still tell there's an and word in there. There should be an and statement. And this one's so simple that I didn't even write anything down because it's really going to take no time at all, because it's not really hard to show this one. But all I need to do in order to prove an and statement, like the one that I've got up here, is to show that both of the claims that are constituting it, P and Q, both of them have to be true. If either one of them is false, then I can stop my work there because it doesn't really matter what the other one is. So now that I've gotten that out of the way and we've returned back to our understanding of and statements from the first panel, let's get this really easy statement dealt with. So, 0 is idempotent. Well, that's not too hard to see, because remember, the definition of idempotence is right here. This is what I'm trying to verify. And in order to get this, I need to know that that is true. Okay. That's just based on the way I've defined idempotent. Something is idempotent if I know that that equation holds with it. Okay, so let's square 0 and see what happens. Well, thankfully, 0 is one of those numbers that it's always really easy to operate with. 0 turns any number, no matter what number it is, into 0 by multiplication. So when I take 0 and multiply it by itself, I'll even write it out to be super explicit. When I take 0 and multiply itself, the only answer that I can get is 0. Which is super convenient because that's exactly what I wanted to prove. Thankfully, the universe and my choice of statements worked out here. Alright, so that is our first claim, the P claim. P is true, where P is 0 is idempotent. Alrighty, so now let's move on to the second claim, that 1 is idempotent. So same deal here. So I'm going to square 1. And now we're going to have to recall for a moment how 1 works when we operate him on others with multiplication. Whenever I take 1 and I multiply something else by 1, 1, unlike 0, which turns everything else into 0, 1 changes nothing. Every time I multiply something else by 1, I have to not change whatever I started out with. It is the identity element of my number system, if I'm to use the advanced algebraic language. So that means when I'm multiplying 1 by 1 here, I can't change the 1 that I'm multiplying. So it has to be 1 afterwards. Yay. That probably didn't need that much explanation either, but now, because we're this low to the bottom, everything really should be explained exactly, and I will start skipping steps and assuming that you got something once we get onto the later material. But that won't happen for a while because, frankly, all of this stuff is easy to miss right up until you leave set theory. Okay, so this is my Q statement. It is clearly true now. And that is all I need in order to show that an AND statement is true. All I need to do to show that an AND statement is true is show that both of its constituent statements are true. And since I picked some really, really easy constituent statements for myself here, that really didn't take any work. Now, in order to do the OR version of this, I've elected not to come up with a new statement for the OR because it would just be something like this, something really silly and small. In order to save time, I will show you the OR statement with this guy just by switching out the AND with an OR. So 0 or 1 are idempotent, which is equivalent if I wanted to say it as P or Q, I would say 0 is idempotent or 1 is idempotent. And like I told you on the very first slide a long time ago, an OR statement is less exclusive than an AND statement. In order to be true, he only needs one of his constituents to be true. And so a proof of an OR statement is the laziest thing ever, because I just pick whichever of the constituents I think is going to be easiest to prove, and I forget the other one. I don't even have to talk about it. It's literally unimportant, because all I'm trying to show is that that statement's true, and I only need one of its constituents. So, I'll take 0, because, well, it was the top of my panel here, and because I like 0. 0 is a great number. So, after I've shown this first statement of my OR, that 0 is in fact idempotent, which is what we got from this line here, then it doesn't matter whether 1 is idempotent or not. This is an OR statement, and one of the constituents is true, so the proof ends right here. And it might be unsatisfying. You might be one of those people who thinks to yourself, well, you know, if both of the things are true, you might as well go off and prove it. And absolutely, you've then proven the AND statement, and that's even stronger, and you can go and use it in stronger situations than the OR statement. But if all you're trying to do is prove an OR statement, well, then all you need to do is show that one of the things is true at any time. So, you know, I go off and I pick the first one here in this case, because I like it, because I like 0, and I show that it's true. But you know, if there were a certain circumstance, because this were, say, a bigger, more compound statement, where it wasn't always true, then this proof still is salvageable. I only need to take the cases where something like this isn't true, and then check the other statement to see if it is true there. Because if it is, then one of the constituents of my OR statement is true, and that's all that's required for an OR statement to be true. So that's the basic procedure for if-thens, nots, ands, and ors. If-then obviously being the most involved because it requires that I assume something and then take a series of steps to prove a conclusion. Not can be fairly direct depending on the thing you choose to prove, or if you're trying to prove the infinitude of primes, you might find yourself having to take recourse, or you might find yourself having to take advantage of proof by contradiction, because otherwise you're going to be sitting there for a very, very long time writing down prime numbers. And then when it comes to proving ands and ors, ands are not as much fun to prove because it means you got to do all the work, but ors are lovely because it means you can do as little work as you like, really. Depends. You're able entirely to choose, up to you, which of the statements you feel like proving. So that's the basic components of all logical arguments. They're basically composed at all times out of ands, ors, if-thens, and nots. And there are, like I said, there are more complicated ways to conjoin logical statements that have other truth tables that I haven't written here. But many of them, and in fact I think actually all of them, can be expressed solely in terms of the operations that I've given you now. So, and that might sound a little strange, but in order to discuss that, in order to prove that claim that I've just made to you now, I'm going to have to wait until next time where I can show you about the idea of logical equivalence. So there's only going to be 2 more episodes on this logic junk before we jump into set theory, because frankly, we don't, there's only so much that you need as a mathematician to go off and apply. We could go forever on 0th order to 1st order and then higher orders of logic, but it's not really helpful if all that you're trying to do is, prove the Pythagorean theorem. So instead of going super, super deep, for the remaining episodes, for the next episode, I'm going to try to work out what logical equivalence is and then show some logical equivalence between a bunch of different statements and the ones that we are using today, and then how this can be used to decode what looks like a complicated argument that isn't made out of the operations that I've been showing you today, how to decode it into an equivalent argument that is very clearly made out of the operations that I showed you today. So that will be the goal of equivalence, and then after that, I simply have to show you how the operation not interacts with all of the other statements. Because he's sort of special, I can take a not of any statement and he will make it into a new type of statement, one that has an equivalent structure that will be important for us to exploit, because there's going to be, oftentimes in the middle of giving a mathematical argument or making a mathematical claim, that your claim is going to sound relatively complicated, because as we've seen a couple times here, in order to write it out as P or Q, I would have to write out 0 is idempotent or 1 is idempotent, meaning I would be wasting a lot of extra time writing words that I don't necessarily need to. So because of that, because we tend to condense our language down, we also have to spend a little time unpacking it every single time, at least until that becomes natural enough that we see exactly what our author is trying to say. So that's where we're going from here. We're going to talk about equivalence and then the effects of knots. And once we've got through that, that will be as much logic as I need to show you folks before we can start learning set theory, which for the moment is the foundations on which all of modern mathematics lies. So that will be next. That will be our language analysis, our little data structure course. And with set theory out of the way, I can finally get you guys to topology, which is what I am waiting for. So I hope you found this informative. I hope it wasn't too long. I wasn't trying to make it as short as I possibly could like I was with some of my differential topology videos. But I still think it probably didn't need to be this long. I was trying to do everything in continuous takes, which is what I'm trying to do here with my new setup. So that is just my short explanation for all of the weirdness and bad editing and poor takes that you will be seeing here. So that is what I'm up to. That is my plan. That's where we're going. I hope you enjoyed. I'll stop talking into this can now, and I will see you folks next time. Enjoy your study break. Stay safe.